Gnanam paramam dheyam. Knowledge is supreme.
So today my theme is to get you to know how to compute Clebsch-Gordan coefficients. This you need to know. Without this, lot of problems in atomic molecular physics, nuclear physics, you will not appreciate. Okay, so this is why the stress in this course is that you should have your hands on in evaluating Clebsch-Gordan coefficients or CG coefficients as it is known. So we have already seen in the last lecture, what have we seen? We've seen uncoupled basis, right? By this I am saying that there are two particles, one with angular momentum J1 and another one with angular momentum J2 with the corresponding magnetic quantum number. You could write a tensor product of these states, which you can equivalently write it as, formally people write J1, J2, M1, M2. Two systems with angular momentum J1 and angular momentum J2. If it belongs to a state J1, M1 and J2, M2, you can take a tensor product. What is the compatible set of operators for this uncoupled state? The compatible set is it's J1 squared, J2 squared, J1Z, J2Z. So this state is a simultaneous eigenstate of all the four operators. If you take J1Z and operate it on J1, J2, M1, M2, that's going to give us M1 H cross, J1, J2, M1, M2. Similarly for J2Z. Is that clear? And J1 squared will give you J1 into J1 plus 1 H cross squared, and similarly J2. So it is a simultaneous eigenstate of this compatible set. Okay. So this was uncoupled basis. And we also had a coupled basis. We had a coupled basis where we had seen some problems, practice problems, where you have spin orbit coupling or you have SC.SP where it is the proton electron system which are interacting. I am sure you have seen some of these problems where there is an interaction between the two systems and interaction between the orbital angular momentum and spin angular momentum, which is a spin orbit coupling. In such cases, it is convenient to work not with the uncoupled basis. In the problem which you did, you know uncoupled basis is not an eigenstate of L dot S, right? I am sure you would have checked this. If you did for the proton electron system, you had taken SP dot SE, and if you try to operate on the uncoupled system, which is the J electron, J proton, M electron, M proton, was it an eigenstate? It was not an eigenstate, especially for ME which is half and MP which is minus half, right? I'm sure you have checked this. So this is not in general equal to the same state with some coefficient. So it is not an eigenstate. The uncoupled basis is not an eigenstate of this. What do we do for that? What is another way of seeing that this will not be an eigenstate? If you take SC Z component operator, the Z component, and you do SC dot SP, what is this commutator? SCZ commutes with SP operators. We don't need to worry about it. What we have to worry about is only the electron spin operator. Does this commute? It doesn't commute. Similarly, if I take the proton operator Z component Sc dot Sp, does this commute? So this is not equal to 0. This is not equal to 0. What about the sum? If you take Sc(z) plus Sp(z) and you do Sc dot Sp, that's the sum of these two. What do you expect? You can show that this is 0. Please check it. Okay, so this is a practice problem. Please check. The sum of these two Z component of the spin operators of the electron and the proton in the electron-proton system, that will commute with the Sc dot Sp. What is this operator? What is this operator? This is the total Z component of the coupled system. So whenever we have coupling like this in the Hamiltonian, it's nicer to work with the compatible set which belongs to the coupled basis. Just trying to motivate you why coupled basis becomes important when there are interactions. So this tells us that the coupled basis will have a total Sz. Formally you can write it as Sc(z) plus Sp(z), but I told you when you operate it on states in the uncoupled basis, you should remember how to do this. It will operate on the electron state only, and it will be an identity operator on the proton state, and here it will be identity operator on the electron state and proton state it will operate. This you should remember. Even though it is not written, this side is on the coupled basis. You don't distinguish what is the magnetic quantum number of the electron, what is the magnetic quantum number of the proton when you look at this side. You only know the total Sz. Is that okay? You don't really resolve what is the individual pieces making up the total Sz. So what is the compatible set for coupled basis? For coupled basis is the total Jz, which is formally you can write it as J1z plus J2z, but you should remember appropriately on this how you should operate. This is one operator. What about compatible set? Second one is J squared, total J squared, and J2 squared. So you can write a compatible set here as J1, J2, semicolon, J and M. And I tried to put, just to remember that it is a coupled basis, I just curved it. It's not necessary, but as long as you remember, it's okay. But this is the coupled basis, which has, it cannot tell me exactly whether the electron spin is magnetic quantum number is what and proton magnetic quantum number is what, but it will tell me the total one. So that is why it's called coupled. You cannot resolve what are the, you can resolve it, but then you need to do the change of basis to go from one to the other. And this change of basis from one to the other is called the Clebsch-Gordan matrix, and we are going to evaluate them today. So this is a simultaneous eigenstate of J1 squared, J2 squared, J squared and Jz. Both are equivalent bases. Why equivalent? The dimensionality of this will be exactly same as the dimensionality of the earlier one, uncoupled base. So just a recap which we did, dimensionality of both the bases are equal. What is the dimensionality? It is 2J1 plus 1 into 2J2 plus 1. The matrix relating the two bases is what we call it as a Clebsch-Gordan matrix. And formally, this is something I wanted to correct, probably I have not corrected it, I should have done this. Okay, so let me write it for completeness, since this is the first time you are learning. So you can take J1, J2, Jm. You can write an identity state here. Okay. So what you can do is, you can take Okay, you understand what I am writing, right? This is an identity state multiplying J1, J2, Jm. This is a complete set of bases. This is an identity operator. So this can be rewritten as summation over M1, M2. You can take this inner product and write. I've just taken this with this and I've brought the kit this side because this is a number. This is for convenience I've used a curve, but actually it is angular only. It's an inner product of two basis state that will give you some kind of a coefficient, and this coefficient is what we call it as a Clebsch-Gordan matrix element. So we write CG matrix element either this way or some books writes it as J1, M1, J2, M2, Jm. So our aim is to evaluate these elements. Our aim is to evaluate the elements of the CG matrix, and that we will do. So the matrix elements are the CG coefficients, which is formally given, and this also we checked in the last lecture. Coefficients is non-zero only when the sum of the magnetic quantum numbers of the uncoupled basis adds up to be the magnetic quantum number of the coupled basis, and this also I said you can work it out by taking the total angular momentum minus the individual z component angular momentum. This is actually 0, and if you substitute, the Jz will prefer to act on this basis, J1z and J2z will act on this basis. You will get M minus M1 minus M2 times the inner product of those two states. That inner product of those two states is the CG coefficient, and that is non-zero only when M is equal to M1 plus M2. Okay. So this is where we stopped in the last lecture. What is the maximum value of M? M max in the total angular momentum cannot exceed J1 plus J2. Is that correct? So we have one basis J1, J2, M1, M2, and then another basis, equivalent basis, which is Jm, which I am putting a curve just to remember it is coupled basis, and CG coefficient is nothing but inner product of J1, J2, M1, M2 with J1, J2, Jm. That is the CG coefficient. And this is non-zero if and only if M1 plus M2 equal to M. Now with this condition, what is M maximum? These states, M1 maximum is J1, M2 maximum is J2, and this condition M1 plus M2 should be M will tell me M maximum cannot exceed, it has to be J1 plus J2. Is that clear? M maximum is the sum of the angular momentum of the two particles. If J1 is particle 1 angular momentum, J2 is particle 2 angular momentum, then the maximum value magnetic quantum number in the coupled basis has to be this. So if you have this to be the maximum, this Jm state is meaningful if J is equal to M maximum, right? So J max also will be J1 plus J2. So we will take that maximum state. Let us take that maximum state J1, J2, J equal to J1 plus J2, M equal to J1 plus J2. This state, this can be achieved only with J1, J2, M1 equal to J1, M2 equal to J2. This is the only possibility. this coefficient we will put it to be 1. This is what we call it as a stretch state or the maximum state. The stretch state in the uncoupled basis is this and the coupled basis is this, and we will equate those two states. That is the starting point. So, the coefficient is Cg coefficient, which relates the stretch state in the coupled basis to the stretch state in the uncoupled basis is 1 always. So, what is this meaning in this language? If you put this to be J1, if you put this to be J2, this will be J1 plus J2 and this will be equal to J1 plus J2. That is the meaning. This is going to be 1. So, that is what I have written here, that we will put the Cg, it is equal to. So, this is uncoupled state and this is coupled state and these two are equated. The m value will decrease from maximum value in steps of 1. So, you reduce from the stretch state by unit 1. How do you do that? You do that by the lowering operator, which is J minus, the total J minus is the coupled basis, and in the uncoupled basis it is J1 minus plus J2 minus. If you do that, you can go reduce your M maximum to M by 1 unit. This is what we are going to do. Okay. So, let us consider a state with a magnetic quantum number which is 1 less than the maximum value. So, that is J1 plus J2 minus 1. Once this M becomes J1 plus J2 minus 1 and we have fixed the total J to be J1 plus J2, that will still allow the state. You agree? It will still allow that state. Okay. So, we can obtain this in two ways. What is the first way? In the uncoupled basis, if you take M1 to be J1 and M2 to be J2 minus 1, that is one way. To get a specific M, M has to be M1 plus M2, M has to be J1 plus J2 minus 1. There are two possibilities. M1 equal to J1, M2 equal to J2 minus 1. Another possibility is M1 is J1 minus 1 and M2 is J2. So, this is a systematic way in which we can keep lowering the steps and seeing what are the degeneracies, which two states can contribute. So, above M values suggest two possibilities for J. This also I said. The total J, this one, it could be J1 plus J2 because that is the stretch state condition. I cannot go above that. Other possibilities, I could also have J to be J1 plus J2 minus 1 because the state Jm permits J to go from minus M to plus M, or M should be less than or equal to J. Is that correct? Any other possibility? So, proceeding this way, you can keep determining all possible degeneracy and states in the uncoupled basis which can contribute to the total magnetic quantum number, which is M. And you cannot go below the total M, it has to be minus J1 minus J2, you cannot exceed that. Agree? If J is J1 plus J2, then you can go from minus J1 plus J2 to plus J1 plus J2 in steps of 1. That is the angular momentum algebra restriction. Suppose we take, just for convenience, you can take both of them to be equal angular momentum, or you can take one of them to be less than the other particle angular momentum. And this kind of degeneracy evaluation which we did here, you can try to do it and you will find that the maximum degeneracy will not exceed the lower angular momentum. Okay, these are checks which you can do. For example, let's take J1 to be 2 and J2 to be 1. This tells me that because J2 is 1, maximum degeneracy has to be 3. This would have said that degeneracy is 5, but when we try to write, we will not exceed the degeneracy as 3 as plotted here in this table. M max is 2 plus 1, which is 3. So M minimum is minus 3. You can go in steps of 1, decreasing steps of 1 till you hit M minimum, which is 2, 1, 0, minus 1, minus 2, minus 3. What are the M1, M2 contribution for a given M? M1 plus M2 should be equal to M, right? You're all following? M1 plus M2 should be equal to M, and that shows that for a specific 3, it's a stretch state. It's one dimensional. If you take M equal to 2, there are two possibilities. You can put M1 to be 2 and M2 to be 0, or the other way round. If you go to M equal to 1, you can have, should remember that M2 will take values from minus 1, 0 and plus 1, and M1 will take values from minus 2, minus 1, 0, plus 1 and 1, 2. You understand, no? So if you take that, then this is the only possibility. This is convincing that if J2 is less than J1, the maximum degeneracy of states which can contribute to a specific M, in this case is 3. So you will not get a degeneracy of 5 anywhere. Just to put your hands and check out for something else also. Take J1 to be 3 by 2 and J2 to be half or something and check it out. What is the degeneracy? Or J1 to be 5 by 2 and J2 to be 1. Check out what is the degeneracy. Just for you to see this table, how the degeneracy is seen. From this data, can we determine J minimum? A degeneracy 3 will kind of indicate that J minimum has some, which is the one which is 3-dimensional. So roughly we know J minimum from this elaborate example, but I have also said as an exercise for you last time, what did I tell you? Use dimensionality to be same for coupled and uncoupled basis. Take the J max to be J1 plus J2 and determine J minimum. That's what I said. So if you do this, just a simple summation, what will you get? So you get this to be the left hand side, and that has to be equated with J max to be J1 plus J2. If you equate it to this, then you can show that J minimum is mod of J1 minus J2. If J2 is less than J1, you could write J1 minus J2. This will also ring the bell that for J1 equal to 2 and J2 equal to 1, J1 minus J2 is 1, and this is 3-dimensional. That's why the degeneracies did not exceed. This is some kind of an indication. But independently, the J value, maximum J value is a sum of those two angular momentum of both the particles. Minimum J value will be the positive of the difference. Okay. If J1 is greater than J2, it's J1 minus J2. That is the minimum J value. If J1 is less than J2, it is J2 minus J2. Clear?